Hello everyone, welcome back to ExpertFunda. Today we are going to solve a really interesting problem from the Leetcode, and the problem number is 2322, and the statement saying that we have to minimize the score after removal on a tree, means minimum score after removals on the tree as a title, and the question statement saying that there is an undirected tree with n nodes. Okay, so it forms a tree, right? And this one combines a approach for the tree traversal, job operations, and some smart observation that we will understand in this problem intuitions. So we'll walk through few examples and then implement the optimization in Java solutions. Okay, so you pause this video and go through the statement so you will understand clearly. But let me read for you. There is a undirected graph, right? There is an undirected tree, you can say, with n nodes that is level from 0 to n-1 and n-1 edges. Means the node we have given, how many n nodes we have given. Let's suppose 5 nodes is given, right? Means the node will start from where we can level them from 0 to 4, right? Means -1. And how many edges will be there to connect n nodes? If this is tree, n-1 edges will be there, right? That is fine. Further, it is saying that you are given a 0 indexed integer array nums of length n. Okay, and it means 1D array we have given, and where nums at I will be nothing but the elements, right? So in the array, and those elements represent the value of ith node. So each index having a node value means ith node value. You are also given 2D integers array that is called edges of length n-1, means the nums and what you call the edges are the two array we have given on the array. So nums contains all the nodes and the edge contains all the edges, right? And you can see further it is saying where edges at I connects two nodes A and B, and there is a difference there is a edge between node A and B in the tree, as I told you. What question saying now? This is the basic things for the tree that we have given. So now the statement remains is our question. Question is saying that remove two distinct edges of the tree to form three connected components. Okay, means we have to remove the two distinct edges of the tree, not the same. Distinct means unique. We have to remove two unique edges of the tree, and we have to form the tree in the connected components, means all the components should be connected. Okay, if you remove the edge of the tree, right, so the remaining should be a connected component. Okay, for a pair of removed edges, right, for a pair of removed edges, the following steps are defined. Right, what you have to do, you have to operate on the tree, means you have to what operate, you have to remove two distinct edges, at least two distinct edges you have to remove from the tree. Means let's suppose the there is, let's suppose 5 was there, so 3 connected components you have to make there, right, to form the 3 connected components. And so that the removed edges will be there, let's suppose 2 remove edges will be there. So what we will do on that? So it is saying first get the job of all the values of the node for each of the 3 components respectively, right? And then difference between the largest job value and the smallest job value is the scope of the pair. It means those pairs that you have removed, right, means the edges that you have removed, that become the pairs, right? And over that we will do job operations. So we will get the job of all the values of the nodes for each of the 3 components respectively, and the difference between the largest job and the smallest job value is the scope of our pair. Okay, for example, let me zoom out a little bit. For example, it is saying, let's say come down a little bit here. Okay, so for example, let's say 3 components have the job node value, let's suppose 4 5 7 1 9 and 3 3. If we'll do the job values over these, we will get 6 8 and 3. The largest value is 8 and the smallest is 3, so the score is 8 minus 3 is 5, right? Means return the minimum score of any possible pair of edge removal on the given tree, right? So if you see this example, what the example is saying that nums we have given this and ages we have given this, right? As you can see here. So if you remove the, let's suppose highlighted one 0 and 1 and 0 1 2, let's suppose we are removing this, so the remaining is become what, 1 3 and 3 4. Can we say that, right? So the diagram explanation is saying that, what is the explanation saying? The diagram above shows a way to make a pair of removals. Means the first component has a node 1 3 4, right? Means this 1 3 and this 4, right? And with the value 5 4 and 11. So its JOR value is, if you take 5 4 and 11 JOR, we'll get 10. Second component has 0 with the value 1 and its JOR value is 1, right? So the third component has 2 and the value we have is 5. So JOR value is 5. So the score is the difference between the largest and the smallest. You can see the largest is 10 and the smallest is 1. So you will do minus, you will get 9. So it can show that no other pair removal will obtain a smaller score than 9. Understand? So like this, we have given another example. You pause this and go through, so you will understand. Okay. Then we have given some constant that we will discuss in the further. Okay. So let's continue and see the slide so you will understand clearly. So as I told you, the question is in the daily Leetcode contest question. So if you have not completed in this month contest, you can go and get the July contest problem and you can start writing the code with the that you have missed. Okay. So let's understand here the minimum score after removals on the tree. So we are given a tree with n nodes. We have, each node has a value that is called nums at I. Each node has a value at the nums at I, means the each node, that is the node in the index in the array. Okay. So that has some value. The tree is given as a list of edges, right? So what is our job? Our job is to remove 2 edges to break the tree into 3 connected components. That is called subtree. Then for each of the 3 component, we have to compute the JOR of its node value. So the score of the removal is maximum JOR among the 3 component minus the minimum JOR, that we know, right? So we will try all the possible pair of edge removals and then we will return the minimum score you can get, right? For example, very shortly I'll say, let's suppose we have given these examples we have given, so it will form the tree like this, right? Means we have like this we have given, and so it will form, right? Because if you see the what you call as we have given 0 1 1 2 1 3 and 3 4, so if you connect all, you will form this tree, right? So if you'll remove the very first edge is 1 and 2, this 1 2, if you'll remove, if you'll break off this node 2, right, and the 3 4, right, if you remove this 3 4, now we have how many components we left is 0 1 and 3, then 2 is alone and 3 is alone, right? Means we have given this tree. Out of this tree, if you remove the 2 edges, so this tree will become in 3 components, right? The very first component become this one. Give me a second. So let's suppose if you will break this edge, which is this edge you will break, another you will break this edge, so it will become how? It will become 0 1 and 3, correct? And 2 is here and 4 is here. Can we say that? So if you'll say the component, so can I say this is a one component, this is one component, this is another component, and this is another component, and all are not connected. So if all these 3 are not connected, means we have how many component? 1 2 and 3. That is why I am saying we have how many components we have? 3 components we have. What are the components are there? 0 1 3 2 and 4. So this problem saying that we remove the 2 edges. So if we will remove the 2 edges, we will build the 3 components. And once you will build these 3 components, what you need to do, your value you have to compute, right? If you compute all these 3 values, right, let's suppose for 0 1 3, right, if you do the computation, JOR computation, what will happen? You will get the JOR 1, 5 and 4. All the JOR if you will apply, you will get 0 here. Similarly, if you will apply for this component and this component, you will get the value. So the max you know, min you know, just you do minus, you will get the value here. Like that, you will try the edge pair until we get the minimum score, right? And one such pair value gives you the score 9. Understand? We'll understand how it will give and what is there. We'll discuss more in this video. Okay. So for the JOR refresher, you think that if you'll take JOR of the two value 1 and 2, you will get 3, and if you'll take 1 and 1, you will get 0, right? So JOR cancel out of the same number, right? So if you are getting the same number, it will cancel, right? And if you'll do the JOR of 2, 2 and 3, right? So it will come 3 because 2, 2 will get cancelled to 0 and 0, 3 will get cancelled to 3 back. So these are the JOR operations. I hope you understand, right? So for example, if we'll take the example, very first example that we are talking about, right? So we know that if we'll form this tree, it will form like this, right? That we know that, right? Means if we'll form this tree, it will look like this, right? So we'll build the tree and we'll form from the edges, right? So it is undirected graph and we are able to form this, right? Because there is no direction there. So now if you level each of its value that we have given in the num, right? So for each value, if you put, so for this 0, the node value become what? 0, then similarly 5, then 2, then 4 and then 11. As you can see in the, we have given each index, we have given its value, and so it will be represented like this. Can we say that? Means we are leveling each node with its value from the nums, right? So what is our goal? Our goal is to remove 2 edges. How many edges? We have to remove 2 edges to break the tree into 3 components. I hope you understand the problem, right? Then we have to compute the JOR of the node value in each component. So how we are going to calculate? So to calculate the score, what you need to do, you will find the max of JOR 1, 2 and 3, or you can say A, B and C, right? And then you will take the mean of the JOR 1 and 2 and 3. I hope you understand the mathematically, right? Now only you if you understand the goal clearly, you can do the do the operations. Only you need to understand how to do that, right? Then you return the minimum score, which is possible. You have to find the minimum score, you have to return it. So let's try one pair of the edge removal, right? So very first, if we'll remove 1, 2 and 3, 4, right? So we are talking about if we have 1, 2, what is the 1, 2? If we are talking, we will remove this one, right? And then 3, 4 means we will remove this one that we are talking about. So in this case, if you'll remove this, the components become is like this, right? So these components, if you operate, right, you will get the values, right? Means the tree breaks into 3 components, component A, B and C, right? If you apply the JOR, if you want to calculate the JOR, right? So for the component, this one, you will find that we are getting 0. For component B, we are getting 5, right? And for component C, we are getting 11. So total score we are getting 11, that we have already seen, right? So another pair we will try to remove the edge 1, 3 and 3, 4, right? So the remaining tree will look like this, correct? So the component we have is 1, 0, 1 and 2, right? So remaining is what? It's a 3, there will be 3 and another will be 4, right? That we have broken. So 3 component will be there, right? So we'll apply the JOR on A, B and C. So JOR A, JOR B and JOR C, if you'll see, we are getting 1, 4 and 11. So if we apply this formula, you will get value 10. Now try another that is optimal. So if you'll remove the S, 0 and 3, right, you will get these components. Similarly, you will find the JOR of A, B and C, right? If you'll do minus, you will get 10, right? So what you need to, you have to find sorry, this is become okay, I'm not updated this one. Okay, so you will get 9 actually. Okay, so for this JOR, if you apply this, you will get the value, right? So 5, 5, 4, C is 11, 0, 1, Okay, I need to the tree. Okay, just apply by yourself. Okay, so what will happen in this approach, you will get if you remove the edges, right, you will get score 9. Okay, and so these three that we have seen, right, you will try operating the, you will removing the 1 2 3 4 and these operations, right, you will get the 9 here. Okay, in this case you will get the 9. Okay, you pause this and you will try by yourself. Okay, so let's summarize, but if you have any doubt, let me know in the comment section. I'll explain it there. Okay, so let's summarize this. So the tree is broken into 3 parts, right? We have to remove 2 edges. Okay, so if you do the JOR, right, on each group nodes value, right, means we have to find the max JOR minus mean JOR, and for each group nodes value we'll apply and we'll find the score. So we'll try all the edge pair and we'll find the mean score, right? So if you talk about the intuition, we are given tree and each node value we have given. What we need to do, we have to remove the 2 edges and we will split into 3 components. Then for each component we'll compute the JOR of all its node value, and so the score is this, and our task is to try all the pair of the edge removal and we'll remove the score that we have seen, right? First of all we'll get some value 10 11 then 9, right, like that we got. So we have to return the minimum score, right? We got the very first, we got let's suppose 11 then 10 then 9. So we'll say okay, 9 is the minimum score, return the minimum 9. So what is our observation? So a tree with n nodes have exactly n minus 1 node. So any tree is there, right? Let's suppose any tree is there. If you remove the component, let's suppose you remove this component or this component, you will get how many component? 1 component, 2 component and 3 component. If you remove, let's suppose any other component is there, right, added there. If you remove, so the left one will become is 3 component, right? So that is obvious. If you remove from the any tree, right, the two edges, the remaining component are 3 components, right? So this is the things you have to understand. But what is our observation? A tree with n nodes has exactly n minus 1 edges. By removing any 2 edges, there will be 3 disjoint connected components. To do this efficiently, we must compute the JOR of any subtree fast, right? So we understand the tree structure which is ancestor of the another, right? So what is our high level approach? Very first, what we need to do, we will build the tree, means we will convert the given edge into adjacency list. Okay, and how you know that, how you do that, you know, in the binary tree or in the graph, right, we used to do that, right? Similarly, for the what you call in the step 2, we'll create a DFS to pre-compute the subtree of JOR. Means for every node we'll compute the JOR of its entire subtree. At the same time, we'll track the Euler's 2 timestamp, so in times and out time will be there, and we'll later check the ancestor relationship in O of 1. Okay, so you can understand what is the Euler 2 timestamp. Okay, in the next step we'll try all the pair of nodes as cut points. So each edge can be represented as a child node, because if we remove the edge between node and its pair, we isolate the child's subtree, right? So how we are going to do, we'll start from 0 to we can say 1 to n, right, and then I plus 1 to this, and we'll keep remove the edge I and edge j. Further, we'll use determine the relationship between the cuts. So there are 3 cases. One subtree is inside another and the subtree are disjoints, right? And so we detect using the Euler 2 timestamp. Let's suppose node U is the ancestor of V, so in U is in the relation less than equal to in V, and for the out you will be like this. Okay, so this is the concept we will use in the Euler store algorithm, right? So next we have to compute the 3 subtree JOR. So depending on its relation between the cuts, first of all, if our subtree is inside another, we'll compute 1 2 and 3, means the smallest subtree, then we have parent subtree and then the child subtree, right? So we'll keep doing that when everything is done, right? So we'll 3 component we will write. then we'll compute the disjoints with the compute 1 and 2 and 3 will come, all the component will compute like this, right? Means the subtree of node j, subtree of j, and remaining is you will take from here. Okay, then finally we'll track the minimum ZOR, where we will have the score of these three and the max and mean score, and you will get the score, and you will just do what the score and the mean score. So we'll keep tracking of the mean score and you will return the mean score. So why we use the subtree JOR? Because if we know the total JOR, right, any subtree JORs, we can get the rest. Means if you know the subtree JOR of a, let's suppose there is a tree, right, and the tree had three component, let's suppose component A, B, and the remaining is C, okay, or remaining. So if you know the JOR value of its subtree A, subtree B, and the remaining, if you apply this JOR, you will get the total JOR, right? So this makes you little easy, or easier you can say. So only you need to know that two subtree and to compute all three, right? What are the data structure that we are going to use? First, agency list we will use to build the tree from the S, then the subtree JOR, and then we will have teen, means the tour in and tour out, and that there will be timer. Okay, so in this case we'll get the complexity of n square. We are trying all the A's pair, that is why we'll get the n square, but the operations we are going to use on this is of 1, thanks to the pre-computed JOR and the ancestor checks, right? And so the space complexity become O of n. So to summarize this, we can say first of all we'll build the tree, then we'll use the DFS, then we'll compute the subtree JOR, then we'll compute in and out timestamp, and then we'll try all the pairs and simulate the cutting edge. So for each, what we need to do, we'll use the ancestor check to determine the relationship, then we'll compute the 3 JOR, and then we'll track the mean max, max minus mean will get, and then we'll return the minimum scope. So before writing the code, either you are in the interview room or you're writing on the here on the Leetcode, right, you should have the summarize in your mind like this, right? Even in the tough interview session, if you are having, right, you should know what are the steps you need to do, right, and then you should start writing the code. Okay, so let's understand on the Leetcode. So very first, what you need to do, you will define all of these three that required, right, and then we have given this mean score, right? You have given nums, we have given as, we have given, right? So first of all, you will build the urgency tree, right? Then you will define this subtree JOR, right? In out will be there. Then you will do the DFS, right? So DFS used to pre-compute the JOR, and for the entry and exit for the ancestor checks, right, you will use the DFS, and then we'll have about JOR, right, total JOR using this, right, and the mean score will use to track the mean score. Now in this step we have to try all the unordered pair of the edges, and for that you will take the for loop, right? You will check if this is ancestor, if else ancestor of these, right, either ij are the ancestor, or if else we have the ancestor ji, right? You will operate all of these, right? You will find the mean score in both of them. If not, then we will find similarly x and y again, and you will find the you will track the mean score again, right? Each time you have to get the score. So these score you have to define, and the DFS you have to define. The very first you will define the DFS, right, and the get score method, and this is just to check the if this is ancestor or not, right? If you have any doubt in this video, let me know in the comment section, okay, and I'll help you there. Thank you guys, thank you for watching this video.